I'll go through the slides, but the solution comes from the two of us. And yeah, it's a third place solution, and we're going to go through the intro, summary, solution overview, and dive into the models which we used. Christoph, do you want to?
Yeah. So I'm Christoph. We are both Kaggle veterans, I would say, Derek and myself. I work at NVIDIA as a deep learning data scientist and part of NVIDIA's Grandmaster team. My background is in mathematics, where I have a PhD with focus on stochastic processes. And on Kaggle, currently, I'm #1 in the world on competitions with over 40 gold medals and a bunch of competitions. And a lot of NLP competitions as well. So I have quite a diverse expertise on Kaggle, I would say.
Okay, good. I'm Dara. I'm an AI research engineer in Doubleyard, which is a edtech company in Japan, and teaches English as a foreign language. That's one of the main focuses. So the competition, as well as all the feedback competitions, were quite interesting for me. I really enjoyed this challenge, and I also have some experience on working on Kaggle competitions over the last few years, and this competition, I think, got me into the top 10 ranking on the competition ranking. So it was nice to have that. So just to go through the information that we had these 11 columns. All of it, I'd say, was quite useful. And as mentioned, the characters were obscured by the letter Q. But early on, we saw that the essays could be reconstructed. I think that was mentioned, to reconstruct what was actually seen as the essay without the actual words. And just to add to the last discussion about this, like I think what the model was learning when, like, this was run through TF-IDF, there was the word lengths, which are, I'd say, important, probably talks about the complexity of words, but also, punctuation, things that, like, Berta mightn't have picked up would be the spaces. We tried adding spaces, but it didn't work. But we did see when we added in line breaks, that helped quite a bit. So there was a few things that which helped here reconstructing. And I know it may not, it's probably better for you if we focused on this sort of thing, but maybe, I guess, when you're looking at trying to help students write, you want to look at how they type, but also a mix of how they type and what they type. So and it would be interesting to hear actually later how you plan to use this. But yeah, we looked at a mix of how they type, so the keystrokes, but also try to elegantly blend that in with what they type, in terms of the essay being reconstructed. So yeah, like was mentioned, one of the, I think, especially on the previous presentation, one of the difficult things for us was the difference between the cross-validation, the leaderboard, and the cross-validation score. So you see it here, like our top models on single models on cross-validation, there wasn't a huge consistency between that and the leaderboard score. So like, for example, this one, would have been maybe our third best model on CV, but it scored pretty poorly on leaderboard, whereas this scored very well on leaderboard, but the CV was bad. In the end, we tried to focus on CV, and I think since we had 3 selections for selecting the final submission, we chose one on best leaderboard, but then mainly focused on CV for the final selections. And I think they're actually what worked best in private. And we use eightfold cross-validation to try and, typically we'd use 5-fold, but use 8-fold here just to try and get a little bit better CV scores. We used 2 different types of models. One was Jupyter on the reconstructed essay, and the second was a mixture of GBM and neural nets on the tabular information on like TF-IDF on the reconstructed essay, or keylog features. You see the weighting of each of these models. So because we had consistency in CV leaderboard scores, so for GBM and neural net type models. So there was like I forget, maybe a 0.02 uplift between GBM between the GBM type models and the leaderboard, but then Jupyter was a lot better on CV than the GBM models, but the leaderboard score was sort of similar. So I'd say both of those, the leaderboard score was similar, but the Jupyter was a lot stronger on cross-validation. And yeah, I think like the private set, we talk a little bit about that later, what we expected in the private set, but depending on how well Jupyter would do, we were thinking that's how well we do on the private leaderboard. So to talk about the Jupyter model, we did MLM pre-training on the Persuade corpus. I'll just talk about these two first points. And we also replaced Q with other characters such as I or X. Just to briefly, I'll go back to this slide. So when we pass this into Jupyter, Jupyter has its own tokenizer to turn this into tokens that goes into the Jupyter model. And there's 2 points on this. One is Jupyter hasn't seen something like this before. It's seen regular text. It has seen full stops and commas. And so it would be able to learn that sort of information, but it hasn't seen this sequence of QQQQs, so it doesn't know how to work with that. So what we did was we took the feedback data set and the public one and changed all the characters to QQQQQ, and then pre-trained with MLM the Jupyter model on that obscured larger data set. And I think the competition data set was 2,500 essays, but the larger feedback data set, the public one, was, I think it's 12,000 essays or something. So there's a lot of data to pre-train it on. The second thing was for the tokenizer, which Jupyter uses, QQQQ doesn't tokenize very well, whereas, and it seems a little bit funny, but I, changing it to I, it does tokenize. It tokenizes much shorter because you don't have tokens in Jupyter for QQ or sorry, or triple Q. You might have a double Q token in Jupyter. So Jupyter only has, I don't know how many tokens it has, if it has 50,000 tokens or something, but there's no QQQ in there. So tokenizing this can turn into quite a lot of tokens, whereas if we change it to I, there's a I token there. And the reason is because of Roman numericals, because the Roman numericals are I. So what that means is if you can tokenize the essay with fewer tokens, because you can create I tokens, then your sequence is smaller. The sequence that you pass into Jupyter is smaller, and then the model can learn faster because it has the same information in a more compact form, so it can learn quicker. And I know this probably isn't, this is a bit of a hack on the competition, so probably isn't useful for you, but it was quite useful for us in doing this. Yeah, another character that worked well was X, changing them out to X. And we also, sorry?
Or maybe you will say this anyway, but it might be interesting to see how we came up with I or X. We basically brute forced through all characters and just saw what characters gives you the least amount of tokens resulting from the tokenizer. And it was I or X, where like I and upper X were like the most optimal single characters that gives you the least amount of tokens.
I think Q was one of the longest, so it actually didn't work really well for Q at all. It was just, yeah, when we switched that. So going along that same vein, we also trained a custom tokenizer on the data. So instead of using the tokens that the Jupyter has learned on, it was originally trained on, we created new tokens based on the competition data set. And it wasn't stronger, but it added diversity. We also trained an event former model. Do you want to say anything to this one?
Yeah, can you go back to the slide with the input data? One back. This one, yeah. So what I was thinking, and I put a lot of effort into this and it didn't work at the end, was to encode each row as one token and use a transformer architecture on this series of events. That's why I would call it event former, basically. So encode the event features, so like action time, just like numerically event, encode the down event with hot rod encoding and so on, and you aggregate all these features for each event, and you have a token for this, and then you create a transformer on the sequence of tokens. But since you have quite a lot of events for each essay, so it might be like 2,000 events or 3,000 events, the model created like this tend to overfit quite quickly, and it's really tricky to train this because you have like 2,000 tokens for each essay, but only 2,000 essays at the end, roughly. That's the scale. So it's really hard to tune this kind of models. So we had one type of this model in our ensemble at the end, which was more focusing on the 3 time features, so downtime, uptime, and also event ID. And this helped in the ensemble at the end, because I think it was not so well used in the other models we used. So that just gives some additional diversity to our ensemble.
So yeah, the CV on these models was around 0.58, and the LB was around 0.585, which was a little bit frustrating, because I think on the XGB, on the other models, the CV was 0.61 and LB was 0.59. So we were really interested on what was going to happen on private when we had a much better CV. We ensembled these using ridge regression. So the ridge regression, we trained with ridge, but took the weights out of ridge and just used that as a sort of a weighted average using those weights. In the end, what we used was Jupyter base with Jupyter large with I, Jupyter base with X. So this was the obscuring character, Jupyter base with the custom tokenizer and the event former. Just to go in sort of a flow of how this was used. So the first thing we did was took the persuade corpus, 26,000 essays, MLM fine-tuned Jupyter based on that. And then that was used for training on the smaller. This model was then used for feature extraction in the smaller model. We did further fine-tune. We didn't freeze this weights in the end, but what we did then was, instead of just training on this, we added in the keystroke information. And I think, like how we pre-trained with obscure characters, it probably doesn't help you a lot, but maybe what can help is how we mixed the keystroke information and the Jupyter model. Like Christoph said, there wasn't a lot of essays and there was a lot of information in the keystrokes. So this tended to overfit, and we did a lot of experiments adding more keystroke information. But in the end, really the best we could get was using the position. So a time series of the position, the time series of the time. So where they are in typing and how long they've taken until that point to type, if you see what I mean. So how far they've got on the essay and how much time they spent to get there. So it's a time series of each of those, and then a time series of the difference to the last keystroke. So this is sort of a delta. So two absolute times on, absolute position, absolute time, and delta of time. This was passed into SqueezeFormer, which is a ASR model for speech. We used this in a previous competition and it worked quite well, so we just lifted the code from there. And again, like we use a simple SqueezeFormer. We tested, it was just one layer SqueezeFormer. We tested out having more layers and so on, but we were just running into overfitting there. And then we took out the hidden layer out of here and just sort of merged merge the output of the Jupyter and this keystroke information with cross attention, and then a linear layer to get the RMSE loss. So it's sort of an attention over, we use, yeah, it's just a attention between between both of those to join them together. Okay. So on the GBM, yeah, we use this is for the GBM and the neural nets. Sorry, the MLP type neural nets. We use the public kernel with 165 features. There was somebody released out a public kernel with 165 features, and it was very strong. And so we just used that. I don't think we created any of our own features on the data set to add in here. And we took a few of the public models and checked their CV scores, and then again use ridge regression. Our thinking was that the diversity of what had been done publicly and the Jupyter model should be enough to get a good solution. But we did invest some time here on making sure that, because there was quite a lot of overfit on the leaderboard, especially in terms of the parameters of the model. So we spent a lot of time working on getting the right parameters of the models, but used the 165 features that was developed for this public kernel. To get the parameters, we fine-tuned with Optuna, and I think, yeah, Cat Boost and Light AutoML. We used the parameters from the public kernel. We did do some tests on these to see if we could improve it, but the public kernel seemed pretty good. And then used a shallow neural net as well. I think that was with PyTorch, just an MLP, or Keras, I'm not sure. One of them to get and again, this was all on tabular data, so those 165 features were tabular data with TF-IDF and so on. Okay, yeah, for the final selection, the GBM and the neural network worked very well on LB. I think that was one of our main things we were thinking about coming up to the end. The Bertha was showing very good CV. GBM and neural net were not showing good CV. They were showing a weaker CV, but they worked very well on leaderboard. So we were getting similar scores on leaderboard for both of those. So we thought that private may work similar to CV, but it seems private worked pretty similar to the public leaderboard in terms of how the models did. So we think there's a slight domain shift between the training and the leaderboard set. So I'm not sure how the public and private data was split, but it could be it was done by topic or year or something like that. Our final submissions were a blend of both parts. I think we mentioned that, a blend of the Bertha and the tabular models. And yep, other insights, the event former, as Christoph mentioned, the event former doesn't work too well, but it was still added to the blend. Any questions?